So I was looking through some logs the other day, and I needed to find about 1,000 different error patterns. And I thought, I'll just write a quick bash loop with grep. 15 minutes later, it's still running. And I'm sitting there thinking, this is ridiculous. There has to be a better way to do this. Then I tried fgrep with all the patterns in a file. Under 1 second. Same search, same file, 1,000 times faster. What's going on here? The naive approach, what I was doing, scans through the entire file once for every single pattern. If you have 1,000 patterns, that's 1,000 passes through the file. Your script is doing 1,000 times more work than it needs to. Instead, fgrep uses Aho-Corasick, which makes just 1 pass. Doesn't matter if you have 10 patterns or 10,000. And that's not even the interesting part. The interesting part is how it pulls this off. This algorithm came out of Bell Labs in 1975. 2 researchers, Aho and Corasick, were working on bibliographic search. They needed to search text for tons of keywords at once, and the obvious approaches were too slow. So they figured out this really elegant solution, and it's been hiding in plain sight ever since. In grep, in virus scanners, in intrusion detection systems. Let's actually see how it works. I'm going to use a simple example to show you the mechanics. We've got the text, "She sells seashells," and we're searching for these patterns. She, he, see, sells, and hell. First thing the algorithm does is build what's called a trie. You start with a root node, then you insert each letter of the pattern. So let's add she. We create an S node from the root, then H from S, then E from H. Mark that E node as an endpoint because she is one of our patterns. Add he. We need an H from root, then an E from that, H. Mark it. Now add C. We already have es from root, so we reuse that. Then we add E from es, then A from that E. Mark the A as an endpoint. For cells, we have es from root. We have E from es. Now we add all, another L, then es. Mark that finals. And hell, we have H from root. We have E from that, H. Now we add all, then another L. Mark it. So you end up with this tree where paths that share prefixes actually share nodes. She and C both start with es, so they share that node. He and hell both start with HE, so they share those 2 nodes. All right, now we start scanning through our text, "She sells seashells." We're at the root. First character is S. Is there an S edge from root? Yeah, there is. We take it. Next character is H. Is there an H edge from es? Yes. We take it. We're now at the SH position. Next is E. There's an E edge. We take it and boom. We're at a marked node. That's our first match. She. Now we hit a space, then es again. Is there an S edge from where we are? Nope. So what do? Just restart at the root? That seems wasteful. And that's exactly the problem we need to solve. That's where failure links come in. And this is the clever bit. For every node in the tree, we compute a link that points to, if the match fails here, where's the longest suffix that's also a prefix in our tree? Let me show you how to actually build these. We use breadth-first search. Start with nodes 1 level deep. They all get failure links to root. Easy. Now for deeper nodes, let's say we're at the E in she. What's the longest proper suffix of she? That would be he. And he exists in our trie. So the failure link from she's E node points to he's E node. Another example, the L in hell. The suffixes are L, LLs, L, and empty string. Do any of these exist as prefixes in our trie? Nope. So this failure link goes to root. Here's the pattern. For a node reached by string S, look at all suffixes of S from longest to shortest. The first one that exists as a path from root in your trie. That's where your failure link goes. These links get computed once using BFS. Takes linear time. Then, during search, they save us from backtracking and help us find overlapping matches. So when we match she, we should also check its failure link to see if he matches. And it does. 2 matches at the same position. When we're scanning shells, we'll match she at the start. then later find hell inside it because the failure links guide us there. Without failure links, when a match fails, you restart from the beginning. You're effectively re-scanning parts of the text. With failure links, you never go backwards in the text. Never. You might follow some links in the automaton to find the right state, but you're not rereading characters from the input. That's why it's linear time. Each character gets looked at exactly once. The actual algorithm is pretty straightforward once you've built the automaton. You start at root. For each character, you check if there's an edge. If not, you follow failure links until you find a state that does have an edge for that character. Then you move to the new state. Check if any patterns in there. Report them if they do. Move to next character. The tricky part isn't the search algorithm. It's understanding why the failure links make this work and why it's still linear time, even though you might follow multiple failure links per character. All right, that's Aho-Corasick. I've got links in the description to the original paper and some implementations you can check out. Thanks for watching.